Okay, in this lecture, we're going to discuss clocks, specifically how there are different types of clock subsystems within microcontrollers and how we can use these. We'll go over the clock sources for the MSP432 and the internal clock signals for the microcontroller. Before we get into those details though, let's first discuss why clocks are so important. So as you all remember from 133 and 233, the vast majority of all computing systems today are built using synchronous logic, where a clock signal is distributed throughout the chip and triggers when registers, memory, finite state machines are enabled to have their state changed. Clocks are also really important for many different types of sensing applications where we're recording measurements from physical systems and want to collect that data and do analysis on them. Clocks are also really important for power. So the way that most embedded systems are designed is so that they are active for only small periods of time. And the vast majority of the time, they are put into a very low power or like a standby state. And these small periods of activity might start because there is some event which triggered an interrupt, or it might also be something that occurs periodically because of a clock. And so these clocks have to be designed, and the system has to be designed so that it can quickly start and stop at different intervals of time. And as we've discussed previously, having these very low power devices is really critical for many embedded systems. And not only because it increases the battery life of these devices, it also enables smaller products, simpler power supplies, simplifies the PCB design, and can improve the overall reliability of the systems. So what is a clock? Well, a clock is really just an oscillator, some device that's oscillating between different states, and a counter, something that's counting those periodic events. And there are a wide range of technologies that we could use to do this, including recording the radioactive decay of an atom and pairing that with a fast electronic counter. And in fact, timekeeping has been around for a very long time. And that's what this graph is showing. Since over 1,000 years ago, the different mechanical devices that were used for keeping time, to within the past century, how there's been a significant increase in our ability to accurately measure time. Some of the oldest clocks from around 500 BC were water-based clocks, where essentially water dripped from some bowl fashioned with certain dimensions and measured to record time. So these are some examples of some early water clocks from China. Now, today, obviously, for the MSP432 and other microcontrollers, we have much more accurate and efficient clocks. But for microcontrollers, they usually have two types of clock sources. One are different types of on-chip oscillators, and the other are based on having oscillators connected to external crystals, a device that has a natural physical resonance frequency after a voltage is applied to it. The advantage of these external crystal oscillators is they offer much higher precisions versus our on-chip oscillators, which are always there and depending on their configurations might have shorter startup delays and lower power. Now with on-the-chip, microcontrollers typically also have flexibility and how these clock sources are connected to internal clock signals, to different pieces of logic within the chip, including the processor and other peripherals, as well as the ability to modify that signal. So they usually include a divider circuit which can alter that clock frequency. And they may also use something called a PLL or a phase lock loop to produce an even wider range of clock rates. The MSP432 has two oscillators connected to an external crystal, one called LFXT and one HFXT, one for low frequency and one for high frequency crystals. The low frequency source LFXT is designed to use a specific frequency crystal at 32.768 kilohertz watch crystal, and the high frequency can be configured for different types of crystals or other resonating devices from 1 megahertz to 48 megahertz. The MSP432 also has 5 internal oscillators, but the most important of those, the one that we'll use the most often, is called the DCO, or the digitally controlled oscillator. This one has the most flexibility and also provides a wide range of clock frequencies. And so here you can see an example. When you look at the schematics for the microcontroller, sometimes you'll see this symbol on the right here signifying that external crystal. So there'll be 2 pins on the microcontroller which you'd connect that crystal to the device and that internal corresponding oscillator. The DCO, the digitally controlled oscillator, is shown down here, and this would have internal control signals which can be modified by the programmer. And in fact, this is what you'll be doing in assignment 2 to change the frequency for those internal clock signals. The clock sources for the MSP432 look like this. We've already seen the LFXT, HFXT, the DCO. There's also a very low power oscillator, and then a couple other higher frequency oscillators with varying characteristics as well, with different power utilizations and startup and stabilization times. The clock signals then, which are connected to different subsystems within the microcontroller, including the processor itself, that ARM processor, look like this. So the master clock, or the MC clock, is that clock that's connected to the microcontroller. There are also other clocks which can be configured to connect to different peripherals on the chip, such as the ADC and the timer. And these include the auxiliary clock, which is the usual source for this, as well as the subsystem clock SM clock, or the HSM subsystem master clock, which are typically higher frequencies to connect to higher speed peripherals on the chip. So within the technical reference manual, you can find several nice diagrams which show the internal configuration, which give an overview of the clocking circuits within the microcontroller. So in this example, we see our internal clock signals, the A clock, the M clock, the SM clock. We have some muxes to select which particular sources, LFXT or the DCO, for example, which can be used to connect to these internal clock signals. And then we also have a divider circuit, which we can use to alter those. Over here on the left, we can see we have this external crystal, for example, for the LFXT clock source, and this internal oscillator. The DCO has several internal control signals that we can use to change the DCO configuration and clock frequency. And so if you look up in the technical reference manual, you'll see several control registers that are associated with that. For example, the CSCTL0 register, which has a parameter here which we can use, DCO R select, the nominal frequency range for the DCO, as well as a tuning parameter that we can use to set those. You can look this up in Chapter 6 in the reference manual, as well as technical note 3 in the lab manual. There's some good tips there. The other thing to note here is that when you're setting the DCO to run at frequencies from 1.5 megahertz to 24 megahertz, your code will look very similar. But the approach for setting the controller to run at 48 megahertz is going to require some additional steps. The DCO for the MSP432 is adjustable for 6 frequency ranges. So those nominal values are 1.5 megahertz, 3 megahertz, 6 megahertz, 12 megahertz, and 24 megahertz. That tuning parameter then can add plus or minus off of that nominal frequency. The code then, and this is found in the lab manual, for accessing the DCO and changing the parameters looks something like this. So the first thing that we need to do is set the key register to the right value so that we can enable or unlock the DCO to access it. So this is a safety mechanism so that if the program started or you had wrong values written into the memory for whatever reason, it wouldn't change the setting. So once we unlock the DCO and these clock system control registers, we're going to set CTL0 to be tunable for 12 megahertz versus the default, which is 3 megahertz. And then CTL1 is used to set the clock sources. So in this case, we're using these predefined macros, which are included in the MSP header files, to set the A clock source and all the other clock sources, including the M clock source for the processor. And then finally, we lock the clock system control registers again. And as I said, for 48 megahertz, there's some good tips in the lab manual, technical note 3. Essentially, before you actually can change the DCO to operate at 48 megahertz, you first need to change the voltage level for the chip. And after waiting a certain amount of delay for that circuit to energize, you'll also need to modify the settings for the flash controller so it has some additional wait states because you're operating at a higher frequency. And then finally, you can do the code for changing the DCO to 48 megahertz. Okay, so now let's talk a little bit how we would insert delays and measure delays within our C program. So there are different ways to do this. One simple way to approach this would be to create a for loop. Depending on the compiler and the options that we have for the compiler, it might produce a different sequence of instructions which results in different delays. So besides just doing a for loop, another alternative which I would recommend that you do is there's a intrinsic C function which the compiler will interpret and generate a sequence of instructions, most likely also a loop, that has a delay for a given number of cycles. And so the delay then that you want to incur would depend on the number of cycles that you want to delay and also the frequency that you're currently operating. Okay, and one last thing. So we're going to be reusing a lot of code throughout the quarter. And in general, it's a good habit to get into is designing modular code. And so what you'll want to do is build a header file and an associated C file for these delay functions. And so you can implement a delay microseconds routine as well as a routine that sets the DCO. And again, technical note 9 in the lab manual has some good tips on this as well. But the basic idea is that you'll put the actual code for those functions within your C source code, for example, delay.c, and then within the header, you'll include the declarations of any macros. For example, you could have a nice macro with the delay cycles to implement your delay microseconds macro, and any other types or declarations. And then as we talked about last week when we saw in the problems, it's a good habit to get into to include header guards within these, and this is the preprocessor directive shown here where we say if this symbol, in this case, in this example, memory H, is not defined, then that means this file has not been included in the compilation process yet, and so the compiler will then incorporate this file, but the very first thing it does is define that symbol so that then later another file will not include the same header file and generate errors later in the compilation.